Hello, everybody. I'm going to talk you through solids and how they're classified based on what they're made out of and how they're held together, essentially. So, first of all, there's different types of solids. There's crystalline solids. We'll talk about the other possibility here called amorphous solids at the end. But crystalline solids, which most solids are, have a repeating pattern once you get down to the lowest level. So these are all examples of metals. So since they're metals, all these would be atoms at this lowest level. But let's say it was an ionic substance like salt, we'd have ions here. Or if it was a molecular substance like water, we'd have molecules at each of these. But regardless, anything that's crystalline has a pattern to it when you get down to the lowest level. These are just a few examples of the patterns. You won't need to know those at all, what the names of those are, but there's just examples of some of the metals in the periodic table and what patterns they make when you get down to the lowest level. So this gist of it is that there's a repeating pattern for any solids that are crystalline once you get down to that lowest level that you can see. There are three types of crystalline solids, and the first type is actually broken down into three more types. So it's a lot to kind of wrap your head around and classify here. So the first one's atomic that I'm going to talk about. Maybe not the first one listed in your book, but the first one I'm talking about are atomic crystalline solids. And they're composite units, or the lowest unit that if you get down there and see that atom or molecule, in this case it's an atom. So there's three types that are atomic. There's metallic, which is made out of metals. Covalent, which would be non-metals. They're actually covalently bonded. So metallic bonding here, covalent bonding, and non-bonding. We'll get into each of these a little bit more specific right away. And I know you have a lot of things to fill in here. So here's the first type of atomic solid. There's a metallic. Talk about that a little bit more in detail. So this would include all the metallic elements. So we've talked about metallic bonding already, in that they have the sea of electrons that is shared within the atoms. But it would also include any alloys. So example of that would be like brass or steel, as you see for examples down here, where we have a mixture of two or more metals. So they are also held together this way to also be considered a metallic solid. They're held together by metallic bonds. We've talked about these properties before. They do have variable melting points. As you know, something like mercury is a liquid at room temperature. That's pretty strange. And we have other metals with very high melting points. So that is quite variable. This is an example of a piece of brass for a trumpet, which is a mixture of copper and zinc. I always get the things mixed up, but brass, I believe, is copper and zinc. So here's just some examples, but really it could be any of the metals and a pretty much endless number of alloys that exist. The next type of atomic solid is called a covalent solid. These are covalently bonded to neighbors. This is very strong because instead of, we're not talking about intermolecular forces here, but like for instance with diamond here, every carbon is bonded to four other carbons with covalent bonds. It's just a huge network of covalent bonds. It's very strong. Graphite is also held together by covalent bonds, but if you look closely here, you can see that each carbon is only bonded to three other carbons. So there are some electrons floating around, and they actually make intermolecular forces between the layers. So if you are writing with a pencil right now, what you have is layers of this graphite that are sliding off and writing onto the paper. So these layers are easily broken from each other, but each one of these would be quite strong. Silicon is also an example of something that would form a network like this diamond would. Last type, that is atomic, are called non-bonding in your book. It's just essentially because they don't bond with metallic or covalent, but the only thing that could hold them together would be dispersion forces. Very, very weak. Very tough to make them a solid, and be easy to melt them and vaporize them if you did ever have them as solid. But you're talking about like noble gases here, that the only thing that would hold them together is dispersion forces, but explanation of how they could become solid is with those dispersion forces. So those are the three types of atomic solids. So that's the only one that is broken down into further examples. The other two types of crystalline. So crystalline in general is atomic, ionic, or molecular. So I'll talk about ionic next. We've talked about this a fair amount already, but positive and negative ions are arranged in a pattern. That's so the positives are closest to the negatives, negatives closest to the positives. They are hard and brittle, as you can see here, high melting points, and are good insulators. As a solid, they do not conduct electricity because those positively charged, negatively charged ions are not able to move around. As a liquid, they could, or if they're dissolved in water, they could, but as a solid, they would not conduct electricity, so they'd be insulators. And I just listed some examples there, but really any positive ion with negative ion would be an ionic solid if it's in its solid form. So again, we have three types of crystalline: atomic, which is broken down into three more, and now ionic, and then the last type of crystalline is called molecular. So these are molecules that are held together by intermolecular forces that we've talked about already: hydrogen bonds, dipole-dipole, and London dispersion. Because they're held together by intermolecular forces, not covalent bonds, not ionic bonds, that makes them a very low melting point, easily vaporized. And some examples would be ice, dry ice, which is solid carbon dioxide, sugar, which you remember from the lab that we did, that sugar melts very easily. That's because the forces that are holding the sugar molecules together are not that strong. So pretty easy to melt them. A lot of them will exist as a liquid or a gas at room temperature. Sugar is an example of something that would actually be a solid at room temperature, but pretty easily melted. So again, three types of crystalline is ionic, molecular, and atomic. And then atomic is broken down individually into metallic, and non-bonding, and covalent. So there's a lot of words to kind of throw together here. And then the last type of a solid is called amorphous, which literally means no shape or without shape. So there's no pattern when you get down to the lowest level. It looks more like a liquid if you could see that lowest level. There's not a repeating pattern. They're just disordered. Even though they're fixed in place, there's not a pattern to them and they're disordered. They don't have a definite melting point. So it's just where they get softer and softer over a certain temperature range, but they wouldn't really have an exact temperature that they melt only at that temperature and stays constant like other solids would at their melting point and plateau at that temperature. Some examples of this would be glass and wax, where those molecules or atoms would be disordered if you got down to that lowest level.